So good afternoon, everyone. Thanks for joining. Our session is New Frontiers in Visual Fidelity, Metrics and Rendering for Media Innovation. And I'm very excited to be hosting this session because we have two new speakers, both of whom are very young, talented engineers from outside the United States, which I think is something our society needs as we move forward into our second century. I'd like to remind everybody, you have QR codes on the walls. Please scan the QR codes and use those to text your questions. I have the app. I will curate the questions, and I will ask our speakers at the ends of their presentations. Our first paper is an efficient quality metric for video frame interpolation, presented by Conall Daly. Mr. Daly received his master's degree from Trinity College, Dublin, Ireland, and is currently undertaking a PhD program as part of the SIG Media Group with a view towards developing more computationally efficient algorithms for video frame interpolation. Conall, please come to stage.
So, good evening. Thank you for coming to the talk, and thank you for the SMPT for inviting me here. My name's Conall. I'm a PhD student at Trinity College Dublin, Ireland, so I'm well used to the weather outside today. I'm funded by Research Ireland and a small Irish startup in video cloud asset management called Overcast HQ. And today's presentation is about creating an efficient perceptual video frame interpolation quality metric. If anybody's not familiar with video frame interpolation, this is kind of a common problem in video processing where we have, say, a sequence at 30 FPS, and we want to, say, slow it down by a half, and we end up with kind of this juddery motion in our sequence. And so we apply a video frame interpolation algorithm, and we get way more frames. So we upsample by 2 times temporally, and you could see that it's a lot smoother. And we can do this again, slow down by half, upsample again, and we get a nice slow motion video that was captured using, say, like a regular consumer camera that normally captures at 30 FPS. And so we want to consider how do we evaluate these frame interpolation algorithms. So VFI algorithms are inherently very motion-based because you can't really do frame interpolation on just a single image. It's inherently based on kind of the sequence of images that you show together. So you're pulling in information from a subsequent frame. And people have noted, particularly at academic conferences and anybody in industry has noted that video quality metrics and image quality metrics are not suitable for evaluating these algorithms. They're not very well correlated with the perceived quality generated by the algorithm. One recently proposed metric that attempts to kind of incorporate temporal consistency into the quality evaluation of video frame interpolation algorithms is flow LPIPs. And this was done by the guys at the Bristol Vision Institute, if anybody's familiar with them. And it's shown to have like really good correlation with differential mean opinion scores with a subjective study that they did. However, it is quite unsuitable for real-time evaluation or training of a deep neural network due to the high computational cost as it relies on neural networks for the evaluation itself. And it's quite high runtime as well. And I'm just going to go into a bit more detail on flow LPIPs. So flow LPIPs is actually based on a modification of LPIPs. Actually, just show hands. Does anybody actually use LPIPs? I highly doubt it, but no. Okay. It was developed by guys at Adobe in 2018, I think, and it's based on kind of this idea. So you can see that we have for phi ref here and phi distorted here, these are two kind of neural networks, and we're actually looking at when you present an image to these neural networks, they sort of generate these activations, which can be kind of similar to, say, firings of neuron in the brain. And we look at the differences between those for our reference or ground truth sequence and our distorted or interpolated sequence. So we're kind of trying to model how humans would kind of perceive the quality of a reference and distorted image. However, the kind of problems itself with this whole idea, but essentially that's what we're doing. Flow pips adds on the modification of trying to incorporate motion information and how this can kind of inform the temporal consistency evaluation of a video frame interpolation algorithm. So you can see on the very far left here, for our reference and distorted sequences, we calculate two motion fields and subtract them to get kind of the differences in between the motion for our interpolated sequence and see how that compares to the motion that we have in our ground truth sequence. And what we wanted to do was say, do we even need all of this neural stuff at all? Can we just strip it back to say, take a simple image quality metric and try and incorporate this temporal consistency into our metric? So we took inspiration from a little bit of work that our group did a while back in 2004 in the area of archival footage restoration. So in this case, if you're, say, scanning in a 35mm print and you have kind of speckles of dust that are getting onto it, you have kind of these impulse artifacts that are being introduced, and you might want to restore this, so missing data treatment. So you want to pull in kind of information from future frames and previous frames and try and remove kind of these dust speckles from your scanned in sequence. However, unfortunately, kind of like there are certain cases of filmed footage that you can kind of confuse with this impulse artifacts. So you can see in the figure on the very far right here, you have cases of motion blurring from helicopter blades or someone making a fast movement, where kind of this can get confused with kind of this speckling or kind of these impulse artifacts. And one way to detect this is to detect the pathological motion within your frame. And our kind of how this developed was that we could measure the divergence of the motion field, which is related kind of to the smoothness of it, and you can pick up on this pathological motion. And we kind of drew an analogy between this and kind of the types of artifacts that were introduced by video frame interpolation algorithms. And so we take this idea of using the motion field divergence to inform video frame interpolation quality. So for anybody not familiar with kind of the vector calculus mathsy bits of it, this is, we have our motion field, which has two components. So the X component U and the Y component V, and the divergence of it is essentially the gradients of it. So we're looking at the changes in our U motion and the changes in our V motion, so horizontal and vertical motion, and we're kind of trying to evaluate how smooth that is. So for cases where the divergence is greater than 0, you're getting kind of diverging motion vectors. For cases where divergence is less than 0, you're getting converging ones. And then for smooth motion, it's just equal to 0. And so we care about kind of these two up here, where it's greater than 0 and less than 0. That's kind of where these temporal inconsistency is present within our frame. And so this is the actual metric that we are proposing, and I'm going to kind of walk you through the reasoning and math behind it. So we have two sequences, our ground truth sequence G and our interpolated sequence G hashed. So I'm just going to walk through. So it's mainly done on G hat. It is what most of our operations are based around. So you can see Z1 up here is kind of like an old school signal processing way of denoting a delay. So we look at the previous frame, calculate our optical flow, so our motion field. We take then the divergence of this. So we use a slightly modified version of the divergence, so we're scaled by the maximum value of the divergence present within the motion field itself. This is just to account for differences kind of in, you could have frames with high motion, so people playing tennis or something like that, or scenes with much lower motion magnitudes. So this is just to scale it into kind of a 0 to 1 scaling. And then we, after this normalization, we perform a binary threshold, so kind of saying cases where divergence is greater or less than this threshold, we indicate as a 0. So that would be a place where we don't detect this kind of pathological motion or temporal inconsistency, and then a 1 otherwise. So we can kind of get this field of 0s and 1s, and then we incorporate this into our image measure. So we're kind of weighting pixel errors based on this temporal inconsistency. And then we sub this into the actual classical PSNR formula. So we're kind of just very familiar, kind of trying not to use any kind of obscure neural methods. It's a very simple kind of a metric. And so that's our metric, and now we wanted to evaluate how well does this correlate with human scores. So we used the Bristol Vision Institute's video frame interpolation dataset. They've done a fantastic job of gathering the data using a subjective study of multiple different frame interpolation algorithms, and there's actually very few subjective quality datasets. So this is why video frame interpolation quality metric development is kind of a challenging. So they gathered all of this data for 540p, 1080p, 30 FPS, 60 FPS, a bunch of different kind of scenarios for video frame interpolation, and kindly provide these human subjective scores along with it so that we can get a correlation with them. And just to give an example of kind of the different frame interpolation algorithms they use. So you have your ground truth sequence up in the very far left there, frame averaging, repeating frames, DVF, which is quite bad, but I have chosen kind of the worst case scenario in interpolating and a 15 FPS sequence up to a 30 FPS sequence. So that's why it looks like that. QVI and STMFnet, which are two quite recent video frame interpolation algorithms, deep learning based. And so then we use a subset of the BVI dataset. So for those 5 algorithms, we choose the cases of interpolating 540p and 1080p sequences, and we choose the scenarios where we're interpolating up to 30 FPS and up to 60 FPS, and we fit our predicted quality scores, so the output of our PSNR div, to the DMOS scores that a human would rate those sequences at, and use the VQuag recommended logistic function as shown here. So it's a 4-parameter model that we then calculate Pearson linear correlation coefficients, so just predicting how well does our metric correlate linearly with the human perception of video quality. Spearman rank correlation coefficient, which kind of measures the monotonicity of the relationship for our quality metric, Kendall rank coefficient, and root mean squared error. So this is the kind of number of different video quality metrics that we compare against. So we compare against classical PSNR, SSIM, gradient magnitude similarity deviation, LPIPs. So those are all kind of image quality metrics. Then we compare against flow LPIPs. PSNR endpoint error, so that's just our using the endpoint error weighting of the mean squared error, similar to how we did the divergence weighting, and then our PSNR div metric on the very bottom here. And then across each of the columns, we look at 540p sequences, 1080p sequences, and then for each of those, we measure Pearson linear correlation and Spearman for interpolating from 15 FPS up to 30 FPS and 30 FPS up to 60 FPS. And then we also have kind of an overall evaluation here, so which shows kind of integrated across all different scenarios how well our metric perform. And I mainly want to draw your attention to flow LPIPs and our PSNR div metric, and you can see that overall we're performing really well, getting a 0.67 Pearson linear correlation and 0.63 Spearman. So it's pretty good, given how simple our metric is compared to flow pips, that we can kind of evaluate this temporal consistency better than flow pips, a neural-based method. And you can see that even when looking at subsets, we mainly are performing pretty well in terms of being more perceptually relevant than flow pips. And now I'm just going to give you kind of a demonstration of how our metric is kind of behaving kind of visually, what's it doing. So for the STM-FNet video frame interpolator, I just picked two sequences here, and I show the value of our PSNR div metric, PSNR SSIM at 12 pips at the bottom of the frames there. And I've shown kind of in red here kind of areas where this kind of temporal inconsistency has been detected, where our motion field divergence is above this threshold that we have picked. And you can see it kind of picks up on areas of motion blurring in the background, or you can see areas of occlusion and uncovering in front of the bike wheel there on the bottom sequence. So this is mainly what I'm picking up on, is kind of these areas where humans are probably going to focus in on kind of these little areas of motion inconsistency. And then just kind of to show, for a case of like a really bad frame interpolator, don't think anybody would ever actually have this kind of bad video frame interpolation quality, but it picks up on kind of this warping and distortion in the frame. So you can see it's much more, there is far more of the frame where this motion field divergence is quite high and is taken more into account in the PSNR div calculation. So you can see PSNR values are around 28, 29 for these sequences, but PSNR div penalizes quite heavily this temporal inconsistency. And so I just want to talk a bit about kind of picking that threshold value where, that's kind of a decision that you have to make. Where's the threshold that we're saying this divergence, this high divergence is where we get this temporal consistency and where we're getting this temporal consistency. So we evaluated using a bunch of different motion estimators for calculating our motion fields and seeing how does this affect the correlation of our PSNR div values. And we kind of did a parameter sweep across the threshold values, and you can see that there is a slight difference between the motion estimator that you pick. So Farmback is a classical-based motion estimator, iterative. PwCnet and RAP are both kind of deep learning-based frame interpolators. RAP probably produces the most accurate motion fields, and you can see that this does cause kind of a reduction in the optimal kind of threshold that you set for detecting this kind of temporal inconsistency. And so kind of choosing this motion divergence threshold is quite important. So I've just shown here kind of for all of the different scenarios of resolution and frame rate that you can get. But kind of picking the threshold value is quite important. And we want to look at more into, is this based on kind of the flow statistics or kind of the motion magnitudes present in the sequence to kind of like increase the correlation scores. And then furthermore, we just explored looking at kind of using a continuous weighting rather than a binary-based threshold. So here we have a kind of a logistic function used to have kind of soft threshold our divergence measure. So we have two parameters, alpha and t, again as previously, and we kind of just varied these to see if kind of adding in a gradual slope rather than a hard binary threshold for our weighting kind of help the correlation scores. And you can see it is quite hard to kind of pick like a particular parameter that works for overall. We do see an increase from 0.67 as previously up to 0.69, but it's probably highly kind of non-linear, non-convex, this kind of optimizing our weighting of motion field divergence. So that's something kind of we want to look more into. And so finally, just to finish up, I'd like to just talk about the key takeaways. So we can perform better than flow LPIPs across all statistical metric using quite a simple, interpretable video quality metric that we developed. We have this beautiful roughly 3 times in terms of run time. So flow LPIPs take 330 milliseconds per frame. We're performing at around 110 milliseconds per frame. So this makes it incredibly suitable for kind of not real-time evaluation, but training deep neural networks for the video frame interpolation task. We use 6 times less memory, so far less VRAM or CPU-based RAM. So we're using roughly 0.2 gigabytes compared to flow LPIP's 1.3 gigabytes. And hopefully we want to use this metric to develop a video frame interpolation algorithm that is more perceptually correlated to how humans would perceive the quality of temporal consistency of algorithms. But so thank you for listening. And any questions?
So we have time for questions, but nobody entered any questions in the app. So, and I do not have them. I don't have a microphone. So,
So, just quick question. So the threshold versus using the logistic function, does that affect the differentiability if your goal is to try to train neural nets with this metric? I assume you want something that's a differentiable metric, right?
Yeah.
Does having the hard threshold affect that?
Yeah, definitely. So that's why we're also looking into kind of using this soft thresholds. Using the logistic function would be far more ideal. I guess we could just use kind of very high values that kind of approximate a binary threshold. Is kind of a hacky way to do it, I guess. But definitely that's an important consideration.
Well, you were obviously very concise and understandable. I congratulate you. Thank you very much, Conall. Thank you very much.